composition of hydrates lab. I'm going to start off by telling you what the purpose of this lab was. The purpose of this lab was a company had asked me to measure out the different amounts of anhydrates slash absorbents slash indicators to put in their packaging for their phones to make sure that they can ensure that the customer will know if there is water damage done to the phone so they can quickly return it and get another phone, and also making sure that the phone is safely delivered. Lab question number 1. Why do you need to heat the crucible before starting? You need to make sure the crucible is dry. So like there's no debris or any residue left in from previous experiences or experiments, my bad. Why do the tongs need to be clean? To ensure that when the crucible is heated, if there's anything left on the tongs, when you put it onto the heated crucible, the residue on the tongs will heat and melt into the crucible, and it could damage the crucible and it could affect your mass. Number 2, why do you need a cover for the crucible? You need to make sure that nothing gets in or comes out of your crucible. So if it's bubbling and popping, you don't want it just bubbling out because then it can affect your mass, or you don't want any just little specks getting down in it because that can just completely throw off your data. Number 3, calculate the anhydrous mass of copper sulfate. So what you're going to do is you're going to take your starting mass and then subtract the how much to find how much H2O was already in the sample, and then you're going to take that divided by the mass of on the periodic table, and we got 0.019 grams a mole of copper sulfate. Number 4, calculate the initial mass of the hydrate. We took the molar mass of copper sulfate from the periodic table and subtracted the mass after the second heating. So mass from the periodic table, mass after the second heating, and we got 1.88 grams. And then to convert that into grams per mole, we take that divided by the periodic table mass, and we got 0.104 grams per mole of H2O. Why did the mass of the sample decrease after heating? Well, because, when you heat something, if it has water in it, the water will evaporate away and it turns into water vapor, and so it, in this case, loses mass. It's pretty much common sense if you just think about it. Number 6, determine the empirical formula. So to do that, we had to take our masses we found in the past few problems and divide by the smaller product, which was our copper sulfate. So here, we divided the answer from our last problem of copper sulfate divided by copper sulfate, and we got 1 because everything divided by itself is 1. So we have 1 copper sulfate, and then we took the mass of the H2O, 0.104, divided by 0.019, and got 5.47 and rounded up to 6 to get to our whole number. Then we got our empirical formula, copper sulfate, 1 copper sulfate for every 6 H2Os. Calculate the percent of water in your sample. To complete this, we had to take our mass of our water, and divide it by the whole sample of the mass. Sorry, 22.71 is not your mass of your water. This is your mass of your water, 4.96. We took that and divided it. Or sorry, no, my bad again. This is the mass of your sample. Mass of your water divided by your sample times 100 to make it a whole percent. 37.90% of water in your sample. Calculate the percent of water in a mole. So this is going purely off the periodic table. To solve this, we calculated the mass of the whole compound, copper sulfate pentahydrate, then found the mass of just the pentahydrate. We proceeded to divide the pentahydrate mass by the whole mass and multiplied by 100 to get your whole percent. So this is all my work. You had 1 copper, 1 sulfur, 9 oxygens, and 10 hydrogens, and so there's all their masses calculated out on the periodic table. That is your total mass, and then you did just the water, which you had 5 oxygens and 10 hydrogens. There's your masses, you add them up, and then you take your water divided by the total times 100 to get your whole percent. 36.08 is your theoretical percentage. And then to calculate the percent error, you have to take your percent minus the theoretical, which is, turned out for me, you got 1.82, and then you take that little difference and divide it by the theoretical, and you get that big old number, multiply it by 100, and you get, I had a 5.04% error. So my recommendation to the company is that I would suggest to use this salt, maybe a little bit more, maybe a little bit less, it just doesn't really matter, because the percent error was an acceptable range. If it was like a 70-80% error, no, do not use this. Your phones will get damaged. But this, it's a very good chance that there won't be any water damage detectable.